Okay, back to the course. I said I was going to review the beginning of this, and that's what I'm going to do. So we're going to start from basic processor design, and for computer architecture, I think it makes a lot of sense to start at the very bottom and work our way up. So we're going to try and talk from physics on the way up. Of course, I'm not going to dive into every single bit because we are not electrical engineers. We're computer scientists, or cybersecurity majors as well. So there might be some hand waving. Different levels of abstraction. Basically, there's different ways to look at what a processor is. The first one we'll look at is we're just going to start with some materials, conductors, insulators, and we're just going to put some conductors, insulators, and semiconductors together, and then we'll have a processor. So conductor permits the electrical current. That means it has a low resistance. Insulator is a poor conductor, meaning it has a very high resistance, and a semiconductor is basically halfway between, but depends on conditions. So it's a variable resistant to current flow depending on what you do to it, aka doping. So making a silicon or semiconductor using silicon. First off, we have silicon, which has 4 electrons on its outer band. When it's put together, they are tightly held. So in general, a silicon lattice, a pure silicon lattice, is considered more of an insulator than anything else. But when we do something to the lattice, we can increase the conductivity to make it a conductor or semiconductor, depending on what we do to it. So N-type doping, we increase the conductivity by adding phosphorus or arsenic. They have one more atom, or electron, which is free to wander. This is called N-type doping because we're adding some negatively charged electrons. So there's phosphorus with an extra electron, and this guy can just freely move about because he's just floating around, I guess, by himself. All right, so this is more of a conductor or semiconductor depending on how much phosphorus we add to the silicon. So if we have just one phosphorus atom and then a ton of silicon, it's not going to be too conductive, but if we add a ton of phosphorus, then it'll be pretty conductive. The other version of doping that increases conductivity is atoms of gallium or boron. And so the idea here is that they have one fewer electron, which creates a hole, and a hole can steal electrons. So you can think of it as kind of pulling or sucking in a spot for an electron. So this atom will accept an electron even though it's one too many, since it fills the 8th electron position in the shell. Again, I'm kind of glancing over a couple things because we're not EE people. So this allows current to flow. All right, real quickly. So one way to make a processor is start with a very pure silicon ingot, aka a cylinder. Slice it up, add some phosphorus or arsenic and gallium or boron, add some metal wires, and boom, we're done. We have a processor. We just got to add it the correct way, of course. So we talked a little bit about you have on your silicon ingot, you have your chips that you can cut off, and then you can package them. And oh, I forgot my show and tell thing again. So I need to, if anyone's in my office in the morning before this class, remind me so I can bring all the different components so you can see what's inside a computer. But in the computer, your CPU will look similar to this, except for it'll have way more of these legs. But each of those legs goes to a port inside of your actual chip, which is packaged usually in some type of plastic or something, some type of material. Okay, so the first thing we talked about, and now we'll start going to the new material. We talked a little bit about how to make a processor, which is really just silicon adding basically phosphorus or boron or gallium to it. The first item we want to make is a transistor, but before we can make a transistor, we need to make a diode. Now, a diode is an electrical structure that only allows current to flow one direction. So, normally on a wire, you could have current flow one way or the other way, but a diode prevents it from going one direction. It can only flow in the other direction. So how are we going to go about doing that? Well, before we get that together, we're going to need to start looking at interesting structure. One that's N-type doped, and the other that's P-type. So the idea here is that you'll have your silicon, but up here you'll add some phosphorus atoms, or maybe down here, and that'll have some free electrons. While down on the p-type, the rest of this is silicon, which makes it essentially an insulator. Over here on the p-type, you have all this as an insulator, and then you'll have some, gallium, which will have some holes in it to go and accept some electrons. And so we're going to have the two set up this way. So notice the n-type, the extra electrons are on top, and p-type, the holes are on the bottom. What happens when we basically smash the two together? Well, there's this junction, and any guesses on what's going to happen?
The free electrons are going to move across the junction.
Right. To the holes at the bottom. So the idea is some of these electrons can start moving to fill in the holes down here. And depending on this zone right here, how close you make it, which forms as a bit of an insulator, because the wider this zone is, the more these electrons have to jump in order to get to the free holes, aka more of a push they need to have. But in general, there's something called the depletion zone, or the equilibrium, where at this point, that many of the electrons can go and fill in this number of holes, but these guys can't make this whole jump because this whole thing has become an insulator. And so they can't jump that far, so to speak. And I'm waving my hands when I say jump, just to make things easier to understand. All right, so with no current, equilibrium occurs, and this is an insulator. Now, what happens if you apply current? Let me start here. From this side going up here. Well, it's going to push electrons because applying current, and then it'll push this depletion zone until they come together like this, and then once they connect, then it becomes a conductor, because you're allowed to flow from the extra electrons here through all the holes here and moving out. Okay? On the other hand, what if you applied current, aka electrons, over here? Well, go ahead.
I was just going to go the other way.
Well,
Right.
it's going to fill in these holes, right? And then these electrons are just chilling up here, and this whole thing becomes an insulator, and therefore it will not allow current to flow the other direction. So this is how we can create a diode. Again, hand waving. Okay. Yes.
Why does it matter which direction? Because it does different things depending on which direction.
Right. So remember, electricity is the flow of electrons. So it's a circuit. So you can either you can think of it as a clock, and think of it as clockwise or anti-clockwise or counterclockwise, whichever way you prefer to pronounce it. But so it's a circuit. So electricity is going to flow one way or the other, and a diode just makes it so it can only flow one direction. And in this case, it'll allow it to flow, electrons to flow from the left to the right, but it can't flow from right to the left because it'll create an insulator if it tries to flow from right to left. But if it goes from left to right, now do notice that you do have to have a certain level of voltage in order to overcome this depletion zone. So if it's like 0.01 volts, it's not going to happen. But if it's enough, the voltage or the push is high enough, then it becomes a conductor and just allows it to flow through. Okay, so that's kind of how a diode works. Now we need to make a transistor. So we're going to do a little trick. We're going to make two diodes back to back. Notice that this N-type and P-type are right here. That's what we have over here, the N-type doping, P-type. So this right here is a diode, and then you can think of it as another diode flipped over here. All right, so what's going to happen here? Well, you have your holes. Obviously, these two electron sides are going to fill in the holes because there's not that much P-type. So in order to make this transistor actually work, we're going to add a ton of P-type to the bottom of it. That way those P-types will actually suck in these extra electrons, and initially this will turn into an insulator because these P-type will, if you apply electricity here, all the P-type will essentially suck it in and not allow it to flow. But we want to turn it into a transistor, so we're going to have something called a gate, which is another input for electricity. The point here is that if you push voltage down here, it'll fill in the holes created here, and that way electricity can flow from here or jump, so to speak, from this N type to that N type and provide some type of connectivity. On the other hand, if the gate's not applied, then there's not enough, you cannot make this jump over this hole, so to speak. Again, waving hands a little. All right, this is the picture we prefer to use. So if there's voltage applied to the drain, to the source, I know that sounds backwards. It is, that's historical reasons. But if you want the electric flow, you have voltage applied to the gate and then voltage applied to the drain. It'll allow electric to flow. On the other hand, if you have voltage just applied to the drain but not to the gate, electricity will not flow. Now, the other option that happens is you turn on the switch, the gate, but you don't have voltage on either side. Of course, you want that to not produce any electricity, because that would be like having a light switch, but you didn't have power going to the light switch anyways, right? So there's no power to go through. So that's another option that does that make some sense? Because you're making a switch, if there's no power to begin with, you want it to be off, even if you're applying power to the gate. All right. So this is our basic building block, because 0, 1, 0 off, 1 is on. And the idea is we can use this in order to make different gates. But let me pause here and say that you can just think of a processor as a ton of these transistors etched on silicon with some wires. Hey, we're done. That's all it is. But as you noticed earlier, what was it? The i7, latest i7 had 40 billion of these things etched together. So you got to figure out the correct way in order to do that. It's a lot. Billion. Although still less than the national debt. Ooh, burn. Okay. Now, everyone be prepared for some really cool 90s graphic. Yeah. Oh man, you like that?
Sure.
All right. Okay, so now we've talked about a transistor. Let me pause for a moment.